When I am using function notation to evaluate a function, I am being given the input x and being asked to find or evaluate the output of the function f of x. And I will do that by plugging in my input x into the function rule. For example, here I have my function rule, f of x equals 3x squared minus 10. And I'm being asked to, often the directions would say, find f of 4. When I'm being asked to find f of 4, that means, as we know, the value inside the parentheses is what is going into my function, my input. So my x is 4, and I just plug 4 into my function rule. So into my function rule, 3x squared minus 10, I plug in 4 for x, 3 times 4 squared minus 10. And then I use order of operations, 4 squared is 16, 3 times 16 is 48 minus 10, and so my output is 38. What this statement says is, given an input of 4, my output is 38. When I plug 4 into my function rule, what I get as an output is 38. So we are often given more than one function rule and being asked to evaluate for particular values of x. So in this first example, a of 6, I'm being asked to find a of 6. That means x equals 6. So I plug in 6 for x. A of 6 is 3 plus 6 squared, order of operations, 3 plus 36, which is 39. So I can just say, okay, my answer is 39, I can box that, or I can have my final answer be written in function notation, the whole statement, a of 6 is 39. So if a of 6, which I'm being asked to find, is 39, but I could also say my final answer is a of 6 equals 39. Either of those is okay. I need to pay attention to which function I am referring to. The function name here is b, so I'm looking at the function rule for b of x, which is 2x minus 4. Here I just know x equals 5, so I plug 5 in for x. So b of 5 is 2 times 5 minus 4, which is 10 minus 4, which is 6. That means my answer is 6. When I plug 5 into my function rule b of x, or my function b, I get an output of 6. That is fine for a final answer. B of 5 equal to 6 is also a great final answer. Still going here, a of negative 7. This is a great example to have because this is a really common place to make a mistake when I have a exponent and a negative value of x. So x is negative 7. A of negative 7 is 3 plus negative 7 squared, which is not negative 49. Negative 7 times negative 7 is positive 49. That means my final output, my output of the function a given an input of negative 7 is 52. So a of negative 7 equals 52. Final example, this is one that is always a little tricky. I have a function rule where c of x equals 17. So if I had my little function machine here, there's my function machine. When I plug in x, all that happens inside that function machine is that my function c converts x into an output of 17. It doesn't matter what x is. I can plug in 73, I can plug in 0, I can plug in negative 4. My output is just 17. So there's no x in my expression on the left, or my expression on the right. Doesn't matter what x is, my output is just 17, and that is my final answer. C of 3 is 17, C of 5 is 17, C of 52 is 17. And again, this is okay, this is a function. It's okay that more than one input has the same output because each input has a predictable output, a very predictable output. That output is 17. I just want to end by referring back to a toolkit from our linear unit. What we're doing here when we are evaluating a function using function notation, this is just using function notation to do what we did in this first part of using linear equations. Here we knew x and we're being asked to find y. So we plugged in our value of x into our equation and got our output. So here x was 6. My equation was y equals 5 plus 2x. So I just plugged in 6 for x. 2 times 6 is 12 plus 5 is 17. and I got my output of y. This is exactly what I'm doing here. I'm just using function notation instead. So instead of saying x equals 6, find y, I'm being told to find f of 4. That tells me, because of my knowledge of function notation, that x equals 4, and I want to find my output, f of 4.